Okay, let's start. So good afternoon, everyone. Welcome to this edition of the mini-school. Today, it's a pleasure to introduce Laure Gouba. She's at the moment at ICTP in Trieste, and in the past, she spent probably several years in South Africa in one role or another. Yeah, so very nice to see you again, Laure. And Laure agreed to give us an introductory school or a mini school on the use of Green's functions for ordinary differential equations. Yeah? And I'm very happy, Laure, that we have a mini school on a specific topic, because my dream is to have courses like yours and slowly building up to a whole overview of everything. Yeah, so thank you very much for choosing a very specific topic, and I see there are lots of people interested in it, and I'm very much looking forward to your lecture. Yeah, and please, you're welcome to share your screen. And the attendees, please, since we are not so many, maybe you're welcome to use the Q&A facility to ask questions, and otherwise, maybe at the end of the talk, you can raise your hand and we give you the opportunity to ask in person. Yeah, so Laura, please, over to you.
Okay, thank you very much, Professor Petitioni, and for introducing me and for the opportunity giving to me to give those mini courses. That is a part of a course of ordinary differential equations and special functions, and I'm happy to do that for the month of October. So I would like also to thank all those assisting and who have assisted for the organizing of the mini course. And thank you for all those attending today, and I hope there will be more later. And yeah, so good afternoon, everyone. And let me start sharing my screen. So for this course, it will be slightly different from probably many the previous NITheCS mini courses, in the sense that it's deal with a lot of equations, and also I will be using probably my a board and the writing to make it as more fit for a course with a lot of equations. So the title of the course is Green Functions for Ordinary Differential Equations. And the goal is to investigate the solution of non-homogeneous second-order differential equations using green functions. And what is the motivation of that? A non-homogeneous second-order differential equation can be solved by the method of variation of constants, where the complete solution of the equation is engendered by one solution of the associated homogeneous equations. And the green function method is an alternative method that can be easily generalized to problems where the method of variation of constant fails. And another motivation is that a green function can be used to reduce the eigenvalue problem associated to differential operator to more tractable eigenvalue problem of an integral operator. Of course, you see that here it comes a differential operator, integral operators, and the next section next week, I will be talking essentially about differential operator and integral operators. And of course, for this mini course, I will not be showing how green function deal with eigenvalue problems, and of course associated to differential and integral operators, but the course is to show how we construct green functions. And keywords are, of course, non-homogeneous second-order differential equations and green functions. So why second order? The most important differential operators which occurs in physical problems are the second order. So that's why if you talk about differential equations, you have to associate to differential operators, and you can have it at various order. But we are more interested to second order due to the fact that physical problems deal more with second order differential operators. Now, since we talk about green functions, I find it interesting to tell you a bit about history about green functions. The history of green function dates back to 1828, when George Green published work in which he sought solution to Poisson equation, that is Laplacian U is equal to F, for the electric potential U defined inside the bounded volume with specified boundary condition on the surface of the volume. And he introduced the function now identified as what Riemann later coined the green functions. So this is a bit of history. And for this mini course, we restrict our discussion to green function for non-homogeneous second order ordinary differential equations. Sometimes here I use more non-homogeneous, but you can also meet inhomogeneous, it's the same. And sometimes I use one inhomogeneous, non-homogeneous, but here I try to keep the word non-homogeneous. And this mini course is for everyone who is interested in the topic, especially the audience can be students at honor levels and the master levels, because it's part of the course of mathematical method for physics. And it's assumed that the audience is familiar with elementary differential and integral calculus. So this is an introduction about the mini course that will take 4 sessions. And now I want to change my board. Okay. So the mini course is organized as follows. So for today, then today we are 5 October. So for today, I will talk about generalities about second order ordinary differential equations. So today I want to talk about things that you already know, I think, and that I will be reminding you. And it's also important if you want to solve a second order differential equation using the method of green function, we should know generalities about second order differential equations. Then next week, that means on the 12th October, I want to tell you about integral operator and differential operators. Because we will be highly playing with integral operator, differential operators. So I found it necessary to dedicate a session to that. Then as a third lesson, that will be on 19 October, then I will talk about green functions. So I means for the third session, I will give you probably how we get green functions, the properties, and how we construct green functions. And the last session, that will be on 26 October, I will give some examples. I mean by examples, how I concretely I have an equation, how I concretely solve using the method of green functions. And then I hope to have time also to discuss about the situation when you have non-homogeneous boundary conditions. Okay, so for a reference, you may find many references because there are many books in the, most of the books that is mathematics for physicists discuss about the method of green function and ordinary differential equation. But here I want to cite here the book of Deneri and Krzyzewski, that's titled Mathematics for Physicists. And the authors are, is a book written by Philippe Deneri and André Krzyzewski. Okay. So you may find this book in your libraries, or also I can provide a PDF file, but it's a PDF file is heavy to give it. It has to, I have to send it through Google Drive. So my contact email, as you already know, or is, you can send me email at laure.gouba@gmail.com. Since the mini course is run 1 hour per sessions, so it may we may lack time for discussions or a lot of questions, but you can still send me questions through emails, and then I may collect and see how I respond to them. Okay, so for today, we will start with generalities about second order differential equations. So for today, first, I will probably say about what is ordinary differential equation. Then I want to remind you about boundary conditions. And since the mini course is about second order differential equation, I want to also recall the non-homogeneous second order linear differential equations. In that, of course, I have to tell you about the associated homogeneous equations. I want to tell you also in point 3 what I mean by fundamental set of solutions. And then I want to briefly say about the method of variations of constant. Brief introduction of the method of variation of constant. In a full course, I would have also first start with showing you how to solve second order linear differential equation using the method of variation of constant. Then once we do the method by green function, then we usually do a comparative study and we see that it gives the same result. And then you see which one is less difficult or more difficult according to, and why it's also good to know how to solve using green functions. So this is what I hope to cover today, and let's see. So ordinary differential equations So an ordinary differential equation of order n is a relation of the form f x u du dx dnu dxn equal to 0. The equation is called a linear differential equation if f, I mean this function that has these as argument, if f is a linear function of its argument u du dx. If I continue, I will do d squared u dx squared, d derivative or the n of u dxn. Okay. And the most general form of a linear differential equation of order n is q of x plus rxu plus s of x du dx plus f of x dnu dxn is equal to 0. Here, q of x is a function of x. R of x is a coefficient of u that is also a function of x. S of x is a coefficient of du dx. It's also a function of x, and so on. This is the most general form, and most of the time you have you can see instead of writing in that way, it's often written like it's the same rx u plus sx du dx plus fx dn dxn u is equal to a function q of x. It's the same, but here I choose to write in that way. Now, what do we call homogeneous equation associated to this linear differential equations? Let's see what we mean by homogeneous equation. In a linear differential equation, if the term q of x, this is my term q of x, okay? If the term q of x, which does not multiply the function ux or one of the derivative of u is 0, the equation is said to be homogeneous. Example, for this case, the homogeneous equation associated to our general form of equation would be a kind of r of x r of x u plus s of x du dx plus f of x dnu dxn is 0. This is an homogeneous equation. Okay. Now, the most general form that we have, if q of x is not 0, then is a non-homogeneous equation. So we should write that. When q of x is different than 0, in that case, the equation is said to be non-homogeneous, and q of x is called the non-homogeneous term. Examples, more example. For example, in a first order differential equation like ax du dx plus bx ux is 0, this is a homogeneous equation. And if I have ax du dx plus bx ux plus c of x is equal to 0, this is a non-homogeneous equation because I have the term c of x that doesn't multiply u and doesn't multiply also the derivative du respect to x. And you will see, for example, that the Poisson equations, in the example I give, the Poisson equation delta u is equal to f. This is a Laplacian of u is f. This is Poisson equations. Is a non-homogeneous equation. While if you have Laplacian of u is equal to 0, the fact that a function f is 0. This is a homogeneous equation, and this is a Laplace equation. So these are examples of homogeneous and non-homogeneous equations. Now let us talk about boundary condition, because these are also terms that appear when you want to solve a differential equation. There are the boundary conditions. Let's consider a linear differential equation of order n, that is a form like qx plus rxu plus sx du dx plus dnu dxn is equal to 0. Of course, I miss the term, the coefficient. Of course, here, if I say it's order n, it means that the coefficient f of x is different from 0. And I assume that x belongs to an interval AB. Okay. So the solution of this equation may not be unique. So first point is that the solution of this equation not be unique. Okay. Additional informations must be given about the function ux and its first n-1 derivatives. This information constitute the so-called boundary conditions. So in order to have a unique solutions, usually you need additional information called boundary conditions. And the boundary conditions may be given in many forms. Okay. The boundary conditions may be given in many forms, and for each form the existence and the uniqueness of a solution must be proved. Okay, so let me give you some examples of boundary conditions. So the idea here is that if you have a linear differential equation of order n, the solution of the equation may not be unique. And the unicity of solutions are often found when you have additional information on the function and its first derivatives, and those additional information are called boundary conditions. But the boundary conditions may have be given in many forms, and I want now to give you some example of boundary condition, how it's given. Example 1. The boundary condition may consist in prescribing the values of the functions ux and its first n minus 1 derivatives at some point x naught in the interval a, b. For example, you may be given the information that u of x0 is a constant c0, and du dx taken at x equal x0 at the point x0 is equal to c1, and dn minus 1 dxn minus 1 u at the point x0 equal to cn minus 1, where c0, c1, cn minus 1 are constants. So this is a kind of information about the value of u at a certain point x0 on the interval AB, and the value of its n minus 1 derivative at the same point. And those information help to have, for example, a uniqueness of the solutions. So I will give another examples of boundary conditions, how it can be set. Example 2. Let's consider the general linear second order differential equation of the form ax d square u dx square, because I said second order, plus bx du dx plus cxu is equal to fx, x belong to an interval AB, And of course, here you have AX different from 0 because we are in the second order. So for this second order differential equation, boundary condition can be of the following form. So the boundary conditions can be of the form, let's say I put B1 for boundary condition 1U equal to, not equal, but the first boundary conditions is given as alpha 1 U A, I am on the interval AB, plus beta 1 du dx at x equal A, plus gamma 1 U at B, plus delta 1 du dx at x equal B is equal to sigma 1. Of course, for these conditions, I have alpha I, but alpha 1, beta 1, gamma 1, delta 1, sigma 1 are constants that we can be specified. And then it's not finished. This is a kind of conditions that we have, and we have also a second second condition, that is boundary 2, condition 2 would be alpha 2 UA plus beta 2 du dx at x equal A plus gamma 2 UB plus delta 2 du dx at x equal B is equal to sigma 2, and of course also alpha 2, beta 2, gamma 2, delta 2, sigma 2 are also constants. So this is, for example, for a second order differential equation, how you can also get a kind of a boundary condition, and this form of boundary condition is different from the form that we have in example 1. And of course, the constant alpha I, beta I, gamma I, delta I, sigma I that you have in these two boundary conditions, I 1, 2, can be specified as long as the equations are linearly independent. Okay. For the moment, I just give you those. I remind you, I think you already know, but I just remind you about those concepts. But of course, when we will be solving, you will see concretely how it works if it seems not to be clear. Now that, for example, you see that in our boundary conditions, we have a sigma 1 and sigma 2. We have here this sigma 1, and we have here sigma 2. And if, for example, a sigma 1 and sigma 2 are equal to 0, then you have homogeneous boundary conditions. Then it's important to notify that. If sigma 1 is equal to sigma 2 is equal to 0, the boundary conditions B1 U, B2 U are said to be homogeneous. For example, when we will, in the fourth lesson, means the last lesson, you will see that to construct, to solve the equations using the green function method is different when the boundary conditions are homogeneous from when the boundary conditions are non-homogeneous. So it's important that I remind you what is homogeneous boundary conditions and non-homogeneous boundary conditions. Okay. If either sigma 1 or sigma 2 or both differ from 0, I mean, if I have, for example, sigma 1 different from 0 and sigma 2 is equal to 0, sigma 1 equal to 0, sigma 2 different from 0, or sigma 1 different from 0, sigma 2 different from 0, if I am in this situation, the boundary conditions are said to be non-homogeneous. Okay, so now what I said so far, I said about a differential equation of order n. I said about when the differential equation is homogeneous, when it's not homogeneous. I also said about boundary conditions that are additional information given in order to have a unique solutions. And then a boundary condition I give can be of many forms. And I give you, for example, 2 examples of how you can find boundary condition. And in the second example, you can see that also there is the notion of homogeneous boundary condition and non-homogeneous boundary conditions. Now that you are set with a bit of generalities, I want now to talk specifically about non-homogeneous second order linear differential equations, because this is what we are interested to. And it is an equation in a general form of ax u dx squared plus bx du dx plus CXU is equal of f of x if, of course, since it's second order, AX is different from 0. Then if you have an equation like that, this is a non-homogeneous second order differential equations. Then the associated homogeneous equations will be of the form AX plus BX du dx plus CXU is equal to 0. This is the associated homogeneous equation, and usually we just say here homogeneous equation. This. Okay. So now for the homogeneous equations for a second order linear differential homogeneous equations, there are two linearly independent solutions, and those solutions are called the fundamental set of solutions. Okay. Two linearly independent solutions of the homogeneous equations that we call U1x, U2x are called a fundamental set of the solutions of a homogeneous equation. So if you are given a let's say a second ordinary linear differential equations, and then you are asked to find the fundamental set of the solutions of the homogeneous equations, it means that you have to set the homogeneous equation associated to this equation that is non-homogeneous, and then the two linearly independent solutions of this homogeneous equation are called the fundamental set of solutions. But then immediately there is a remark. The remark is that because the homogeneous equation is linear, then the linear combination of the solution U1, U2 will also be a solution of the homogeneous equations. So this is the first remark. Because of the linearity of the homogeneous equations, the linear combination that I call C1 U1x plus C2 U2x, where C1 C2 are constant is also the solutions of the homogeneous equation. This is the point. And then there is a theorem that I will not demonstrate. The theorem is saying that the most general solution of the homogeneous equation of course of second order is of the form ux is C1 U1x plus C2 U2x. Of course, C1, C2 are constant, arbitrary, can be even complex number, are arbitrary complex constants, and U1, U2 are a fundamental set of solutions. And with respect to this theorem, now what is the general solution for the second order non-homogeneous differential equation? This I give another theorem. I call it 1, theorem 2. The most general solution of the second order non-homogeneous equation non-homogeneous differential equation ax d square u dx square plus bx du dx plus cx u is equal f of x is of the form ux, the solution is of the form ux, c1 u1x plus c2 u2x plus upx, where u1, u2 are a fundamental set of solutions of the associated homogeneous equation, and UP is any particular solution of the non-homogeneous equations. Okay, and of course, C1, C2 are arbitrary complex constant. Okay, so the question is, how do you find U1, U2, UP? And usually that comes the point of using various methods. And I think most of you also know the method of variation of constant that we'll not discuss for this mini course, but we want rather to see how we solve the equation using the green function method. But even the green function method, you have to know the fundamental set of equations. And the fundamental set of equations, you can always know when you have a knowledge of one solution. Knowing only one solution of the homogeneous equation through the method of variation allow you to know the second solution and have then the fundamental set of solution. And to find the particular solution, you have to use a method of variation of functions like the one you do to have the second solution U2 and to get it. But in the green function method, we don't look for, we don't use this long way of finding the particular solutions. And it fits with higher derivative problems and partial derivative problems where the method of variation of function fails. And that is the motivation of using a green function method. But yet the story is not finished, but because you have to find one solution, and sometimes it's not easy to find the first solution except for some simple cases. For example, some simple cases, you can guess and you can find easily one solution and generate the others. But when it's complicated, you cannot find it analytically, and then you have to use another method called the method of Frobenius. So, Professor Pituccioni, I think it's 3. Do I have more time or should I stop here?
Laure, I think I would, sorry, I was on mute and I forgot. I would suggest you would imagine that after 2 years and more of COVID, we would know to press the microphone. I would suggest that this looks to me like a good spot to stop for today. You know, the past experience shows that, you know, after 1 hour, people stop focusing, and I think we already lost one participant in the last few minutes. So if you don't mind, we can stop here for now.
It's a good point. We can stop here.
Yeah, and we can ask the participants if they have questions.